Hello, this is J. Jegadeeshwaran participating in DRDC 2021. The given mission statement and the constraints are shown here, and the proposed design is made adhering to these given guidelines. So, these are the constraints, and so how did I design? So, in this video, we will see how my design was made. So, the very first component in the design was the rocket motor because depending on its size, only other components can be made in open rocket. So, the rocket motor was chosen based on these parameters. The first one is the specific impulse, which says for a given amount of propellant flow, how much thrust is produced, which is basically the efficiency of any rocket motor. So the next one is the structural ratio or coefficient, which says how much uh, non-propelling weight, that is the structural weight, is there in the motor. So this should be less because we don't want unnecessary weight, right? So then comes the burn time, that is for a given rocket to reach maximum altitude, the amount of time in which the thrust is acting on the model should be very high. Then only it will go to uh, high altitude. Um, so we need high specific impulse, that is ISP, and burn time, but low structural coefficient. So to find out which has these properties, that is which motor in open rocket has these properties, uh, following the guidelines, I tabulated all the G class motors like this in an Excel sheet. So, uh, and I calculated all these parameters. That is the burn time, structural ratio, then propellant mass, specific impulse, and something called as effective ratio. I will tell what it is. So, uh, these details are available in open bracket, right? So the structural ratio should be very less. So green implies it is very less, and red means it is uh, very high. So here burn time is we need high burn time. So uh, high burn time is marked as green here, 8.5, and the low are marked as red here. So specific impulse, we need high specific impulse. So high specific impulse is marked as green. So all the green parameters are good. So one motor will have high burn time, another motor will have high specific impulse, right? So we need to have a trade-off between these motors. So what I did is I made an effective ratio, which means I just multiplied the burn time and specific impulse and divided it with the structural ratio. That means the denominator value should be less and the numerator values will be high for the effective ratio. That means uh, it will give the maximum value uh, for the effective combination of these parameters. So the maximum value for effective ratio in all these configurations, that is chosen as the design target for my solution here. So uh, if we see all these things, the effective ratio is highest for these 87.2 impulse motor. That is uh, the one with 8.54902. That is the burning time. That motor was chosen. So we'll go to the next slide. So this motor, the name is Aerotech G12RC. It has 87 total 87.2 Newton seconds. Average thrust is around 10.2 Newton. And if you see the thrust time curve, it is also very good. Like it is very predictable. And most of the time, the thrust lies within the 10 around 10 Newton value. So this motor was chosen for this design. So compared to other motors, 10 Newton is less. So the structural loading on the rocket will be very less compared to other motors. Therefore, we need not go for very high strength material which will increase the body weight of the rocket. So this is the final design of the rocket. The nose was designed to have minimum drag while having continuity with the body tube. The body tube length was kept accordingly to have apogee at high altitude and at the same time having enough strength and space to hold and carry other components. The fins are designed to produce at least drag, but also maintaining the stability by bringing the center of pressure to the back. The location of CG is at 21.8 centimeter and the center of pressure CP is at 27.3 centimeter. If we calculate static margin, it is coming around 5.5 centimeter, which gives a stability of 1.53 caliber. So the design parameters are tabulated in this slide. So every component is designed to have enough strength to hold everything in its location rigidly. The this shape, size, and dimensions are given here. So coming to the simulations, the final design was tested for payloads ranging from 50 grams to 120 grams with a step size of 10 grams. The rocket is stable for all the payloads, and the maximum altitude is 1461 meter, that is 1461 meter for the payload of 50 grams, and the maximum payload tested was around sorry, the maximum payload that is tested here is 120 gram for an altitude of 1232 meter. So also the maximum acceleration and velocity is very less compared to other motors that I have tested from the G class. So for the same altitude, which means the load due to gravity and aerodynamics forces are very less compared to other motors in this configuration. So this is the flight profile with respect to time, which is very self-explanatory, and um, this is the stability time graph. We can see that the CP and CG are far enough, and the CP is aft of CG throughout the flight time, and stability margin is high around 1.9 to 2 caliber during the flight. So uh, this is the design that is proposed by me. So the mass of the rocket is 354 gram, including the payload mass of 120 gram. The payload ratio is very high, and the mass ratio is very less, which is desired in rockets. So it can take 120 grams payload to 1200 meter altitude and 50 grams to 1460 meter altitude. And uh, from the slides we can see all the constraints are satisfied and the technical feasibility is also explained. uh, that is the component strength and dimensions accordingly we have shown. So I believe I have defended the design as per the judging criteria provided in the um, uh, problem statement given by DRDC. Uh, Sorry, given by STNX. So thank you.